Hi everybody, welcome to your first AP Chem podcast. This is for Chapter 3 to review some skills and to learn some new skills in creating empirical formulas. All right, first this is a diagram that shows you the steps needed to develop an empirical formula. You did this a ton of times last year, but here's a little shorthand that Kermit will help you remember how to remember the process. He says, percent to mass, mass to mole, divide by small, multiply till whole. With those wise words, let's try a practice problem. So we have some PABA, para-aminobenzoic acid, that we'd like to find the empirical formula for. Here is the data, and first step, percent to mass. All right, so we've got percent compositions. We're going to assume those are gram numbers, and we're going to divide them by their molar masses to get the moles of each. Okay, so we went percent to mass, mass to mole. Divide by small. That means divide each of the moles by the smallest number of moles, which in this case would be nitrogen. Divide each one of those so that we have something to 1. So as we divide those all by the moles of nitrogen, we end up with 1 nitrogen, which is proportional to 7 carbons, 7 hydrogens, and 2 oxygens. Therefore, the formula is C7H7NO2, PABA. All right, that should be quite familiar to you from last year. And if you're having any troubles with this, please come to a tutorial and get some help. All right. So let's try another one. We have ascorbic acid, which contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. Pause this video and find the empirical formula of vitamin C. Okay, your answer should be C3H4O3. Hope you got it right. All right, so now, Beaker's like, that's pretty easy. But, as Bunsen says, not so fast. They're not always the way the molecule exists, so we have to do something else. Hang on, Beaker. It's not that hard. All you have to do is divide the molecular mass by the empirical mass to determine the multiplier to get the molecular formula. So let's try an example to determine a molecular formula. Mesitylene, a hydrocarbon that occurs in small amounts in crude oil, has an empirical formula of C3H4. The empirically determined molecular weight of the substance is 121. What's the molecular formula? All right, let's do a problem. So we want to take the molecular formula. Mesitylene is a hydrocarbon that's in crude oil. It has an empirical formula of C3H4. We are going to use Bunsen's information to try to determine what the molecular formula is. So we need to take the empirical formula, 121, and divide it by the mass of the molecular formula. So it's going to be 3 times 12, 36, plus 4, which is going to be 40. So if we divide that out, I think we can see that that's approximately 3. And that means that we would take 3 times our empirical formula to get the molecular formula, C9H12. I'll rate this like approximately 3. All right, next, combustion analysis. Sometimes it's difficult to get a particular mass of each element for a compound. So one way to get around that is to use combustion analysis. Get my pen on again. we take a compound, and if you burn it, and then trap the water, trap the carbon dioxide so that you can get a detailed analysis of those particular compounds, then you can tease out the particular elements and their amounts to figure out the empirical formula. Let's go through an example. All right, so we have caproic acid, which is responsible for the foul odor of dirty socks. You always wondered about that, didn't you? It's got just carbon, hydrogen, and oxygen. And if you combust it, you get 0.255 grams of the compound. If you combust that much, I'm going to make notes of the numbers. And then once you combust it, you're able to trap, 0.209 grams of water and 512 grams of CO2. So that was trapped in this part. And then any unused oxygen leaves. So what can we determine from this? So if we have the water here and the CO2 here, and this had C, H, and O to start, that means that if we only added oxygen, we could see that all of the hydrogen from the compound is in the water. All of the carbon from the compound is in the CO2. So that gives us some options. So I'm going to change my color here. Let's use some red. So if we focus on the water, for instance, we know we have 0.209 grams H2O. And I can change that to moles so that we can then figure out how many moles of hydrogen we have. So if we have 18 grams of water in 1 mole, and then I multiply that by 2 moles of hydrogen for every 1 mole of H2O. Sorry about the mess. Then I can tell that I have 0.0232 moles of hydrogen. Hopefully you got the same number. Then we can find out how much carbon we have. Start with 0.512 grams of CO2. And I'm going to change that to moles. I always want to work in moles. Haven't done this in a while, so apologize for my handwriting on the tablet. There's 1 mole of carbon for every 1 mole of CO2. So that gives us, previously calculated, 0.0116 moles of carbon. That's really interesting. All right, so now we know our moles of hydrogen, our moles of carbon. We still need the moles of oxygen. And because we added oxygen, we cannot just calculate it the way we did the hydrogen and carbon. But we do know the original mass. So if we can subtract out the mass of the carbon and the mass of the hydrogen, we'll have the mass of the oxygen. I'm not going to show this work, but you can trust me that I changed the 0.0232 moles of hydrogen to grams, and that one's easy enough, 0.232, grams of hydrogen. And I changed the carbon to grams, and that is 0.140 grams of carbon, which leaves you with, please check my math, 0.140 0.063 grams of oxygen. Yay! So now what you have to do is determine moles of oxygen and find the empirical formula. Pause the video for a second and get the answer. All right, you should have found that you had point 0.03875 moles of oxygen. Divide by the smallest and you get a ratio of 3 to 6 to 0. All right, moving on. Let me know if you have trouble with the combustion analysis. You'll be doing some homework on this over the weekend. Okay, now we know the empirical formula, 3C3H6O, and to find the molecular formula, we need to compare the molar mass of the molecule to the molar mass of the compound. That answer should be C6H12O2. Isn't that funny? That's the same formula as sugar. Must be something different because it certainly doesn't smell like sugar. All right. Let's do a practice problem on hydrate formulas. In your handout, you do have directions to walk you through it. It's again, find the moles, but this time you're going to find the mass and moles of the anhydrous salts and the water molecules. And then you're going to find the mole ratio of those two parts. So let's walk through a problem. So in this case, we know the original mass was 2.50 grams of the hydrate, and we have 1.59 grams of the anhydrous copper sulfate. So the difference, 2.50 minus 1.59, is a difference of 0.91 grams that can be attributed to water that was driven off. So then you can find, this is the CuSO4. Then you can find the moles of each. 0.91 grams of water, divide by 18 grams, is 0.051 moles of water. All right, let's change the pen color. Oh, this is particularly hard. Let's try blue this time. Oh well, I'll stay with red. Forget it. We have 1.59 grams of copper sulfate. The molar mass of that is 159.6 grams. And that leaves us, when I round off for sig figs, I believe 0.0100 moles of copper sulfate. Okay, so we want bigger divided by smaller. So we're going to take the water, there should be more water molecules, divide it by the copper sulfate. You could probably do this in your head because it's always going to be a whole number, but you would take 0.051 divided by 0.010, and we should end up with the formula of, oh, it's on your handout actually, isn't it? It's copper sulfate pentahydrate. CuSO4.5H2O, copper sulfate pentahydrate. All right, next, limiting reactants. Let's talk cookies. If you look at this set of ingredients here and you look at the recipe, you could do the math, but I bet if you look at the containers, you have a box of butter, you have some sugar, you have lots of flour and eggs and milk. You can see that one of these ingredients is going to run out before the others. To me, it looks like the sugar is going to run out first. And that would be the limiting reactant. It's going to limit how many cookies you want to make because without enough sugar, they're not going to taste that good. So the limiting reactant is what's going to run out first. And it's in the smallest stoichiometric amount, so that means we're going to have to do some stoichiometry. In the example below, the oxygen would be excess. And you can see if you're making water, you've got 1, 2, 3, 4, 5, 6, 7 oxygens to 10 hydrogens. Since we know we need 2 hydrogens to every 1 oxygen, that means when all the hydrogen's gone, 5 of the oxygens will be used up as a 2-to-1 ratio. And so our leftover excess reactant is 2 molecules of oxygen. So let's do that with something a little more complicated. We've got the reaction between aluminum and chlorine to make aluminum chloride. If we have a mixture of 1.50 moles of aluminum and 3 moles of chlorine, and they're allowed to react, what's the limiting reactant? All right, so we are given moles, which makes this a little bit easier. We have a 2-to-1 ratio, so if we have 1.50 moles of aluminum, my question is, how much chlorine do we need, and do we have enough or do we have an excess? So I can just do a stoichiometric ratio. I need 3 moles of chlorine to every 2 moles of aluminum. And when I do the math, that's 4.5 divided by 2. That gives me 2.25 moles of chlorine needed. That's really important that you realize that's what you need. Now you have 3 moles. So that tells you, think about it, which one's going to run out first. In this case, it will be the aluminum because you have plenty of chlorine to use up all of the aluminum. So, limiting reactant is aluminum. So now, how many moles of aluminum chloride are you going to make? So, let's try cyan. If we know that 1.50 moles of aluminum is going to limit or determine the amount of product made, I'm going to use it to determine how many moles of aluminum chloride by using the stoichiometric ratio. And it's a 2-to-2 ratio, so this one's pretty easy. So we will get 1.50 moles of aluminum chloride. That is correct. It's always nice when things work out that way. Now, lastly, how many moles of excess reactant remain? What color can we use this time? Let's try black. So we know that we have 3 moles of chlorine, and this is the excess reactant. And we needed 2.25 moles of chlorine. That leaves us with an excess, my shorthand, of 0.75 moles of chlorine. Wow, that looks terrible. But luckily I have it in type 2. All right. Hopefully that refreshes your memory a little bit. You will sometimes be given grams and have to determine grams, but that's just that one more step in stoichiometry that I know you can handle. All right, theoretical yield, maximum amount of product that can be made. In our lab, we'll have some idea of how much we can make theoretically. And then the actual yield is often different. It's often a little bit less because, as we've talked about, you always lose some in the process and in the transfer. Then you want to find percent yield by comparing the actual to the theoretical, because knowing exactly how much you got isn't that useful, but you want to know what percent you got so you can use that to predict for future work. So here's a refresher on the percent yield calculation. Now you have some sample exercises in your book that you can try. I'm going to go through these and show you the answers so that you have them, but I want you to try them on your own. So adipic acid is used to produce nylon. It's made commercially by a controlled reaction between cyclohexane and oxygen. So here's the reaction. Probably, well, you could have done that because you could see that water was left over, but you don't have to. Okay, assume that you want to carry this reaction out, starting with 25 grams of cyclohexane, and that cyclohexane is the limiting reactant. All right, so you start with this, find the adipic acid theoretical yield by doing your stoichiometry, and you should get 43.5 grams. So if you haven't paused and done that, do that and make sure you can get the right answer. And then if you actually get 33.5 grams of adipic acid, what's the percent yield? So this is where you compare your theoretical yield to what you actually got. Remember, it's actual over theoretical times 100. You should get 77%. All right, that's all for today. Hope these are going well. If not, please come in and get some help in tutorial. Have a great day.